UGC 12158 lies hundreds of millions of light-years away, yet its structure feels strangely familiar. This barred spiral galaxy unfurls sweeping arms from a central bar of stars and gas, echoing the same architecture astronomers map within our own Milky Way. The luminous bar channels interstellar material inward, feeding both star formation and, potentially, an active nucleus. Spiral arms arch outward in a graceful symmetry, dotted with knots of young blue stars and punctuated by dark lanes of dust that absorb and scatter starlight. Its resemblance to our home galaxy makes it a valuable reference point for understanding the Milky Way's shape and dynamics, since our inside perspective hides much of its overall form. By studying UGC 12158's rotation, stellar populations, and interstellar medium, astronomers can refine models of how barred spirals evolve, how their arms persist, and how central bars influence galactic metabolism over billions of years. Each observation offers not just a view of a distant stellar city, but a mirror that reflects the possible past and future of the galaxy we inhabit. UGC 12158, located in the constellation Pegasus, has drawn the attention of astronomers not only for its visual beauty but for its remarkable similarity to the structure of the Milky Way. Classified as a barred spiral galaxy, SBBC type, it exhibits a well-defined central bar from which two primary spiral arms emanate, gradually branching into a complex network of secondary arms and spurs. Observations conducted in optical wavelengths reveal bright, massive star-forming regions concentrated along these arms, while near-infrared imaging uncovers the older stellar populations that dominate the bar and inner bulge. This multi-wavelength approach allows researchers to trace the distribution of both young, hot stars and ancient, cooler stars, providing a comprehensive picture of the galaxy's stellar evolution. Spectroscopic studies using large ground-based telescopes, such as the Very Large Telescope, VLT, have mapped the rotational velocity curve of UGC 12158, indicating a substantial dark matter halo extending well beyond the visible disk. The rotation curve remains flat at large radii, a signature trait of massive spiral galaxies, suggesting that a significant fraction of its total mass is in the form of non-luminous matter. By comparing these measurements with dynamical models of the Milky Way, scientists are able to estimate the scale length of the disk, the pattern speed of the bar, and the rate of spiral arm winding, parameters that are otherwise difficult to measure for our own galaxy due to our embedded vantage point. The interstellar medium within UGC 12158 has also been the subject of detailed investigation. Radio observations in the 21 cm line of neutral hydrogen, HI, show that the gas disk extends far beyond the stellar disk, indicating a large reservoir of star-forming material. Furthermore, millimeter-wave observations with ALMA detect molecular gas, primarily CO, concentrated in the central kiloparsecs and along the bar. This gas distribution correlates with enhanced star formation rates measured via far-ultraviolet and H-alpha emission, confirming the bar's role in funneling gas inward, where it can collapse into new generations of stars. These findings parallel similar processes hypothesized in the Milky Way, where the galactic bar is believed to drive gas into the central molecular zone. One of the most notable events associated with UGC 12158 is the Type Ia supernova SN 2005 CF, which occurred in one of its spiral arms. This event was extensively monitored across the electromagnetic spectrum and has since become a calibrator in cosmological distance measurements due to its relative proximity and low foreground extinction. The supernova's light curve and spectra have contributed to refining the standardization of Type Ia supernovae as distance indicators, which are crucial for determining the Hubble constant and constraining the expansion history of the universe. In terms of stellar populations, photometric analyses reveal a metallicity gradient across the disk, decreasing with distance from the galactic center. This gradient reflects the history of chemical enrichment driven by generations of supernovae and stellar winds. The central bulge and bar regions exhibit higher metallicities, consistent with prolonged star formation and enrichment, while the outer arms preserve more pristine, metal-poor material. These trends mirror those seen in the Milky Way, further reinforcing UGC 12158's status as a structural and evolutionary analog. Simulations of barred spiral galaxies that match UGC 12158's morphology suggest that its bar likely formed several billion years ago, possibly triggered by tidal interactions with smaller companion galaxies. Although no major companions are currently observed in its immediate vicinity, subtle asymmetries in its outer spiral arms and gas distribution hint at past gravitational encounters. Such interactions can enhance bar formation and drive secular evolution, reshaping the galaxy's internal dynamics over cosmological timescales. In studying UGC 12158, astronomers gain not only a window into the dynamics and structure of a typical barred spiral galaxy but also a proxy through which the hidden face of the Milky Way can be inferred. Each spectral line measurement, each high-resolution image, and each dynamical model adds a layer of understanding to the complex processes that govern galactic evolution. This distant galaxy serves as both a laboratory and a mirror, reflecting the potential past and future of our cosmic home. High-resolution imaging of UGC 12158 from the Hubble Space Telescope has provided unprecedented detail on the distribution of star clusters, dust lanes, and the intricate filamentary structures within its spiral arms. The data reveal that the dust lanes are sharply defined along the leading edges of the arms, where density waves compress the interstellar medium, triggering bursts of star formation. The youngest clusters, composed of hot, massive O and B-type stars, are seen slightly downstream from these dust lanes, consistent with the predicted time delay between gas compression and star formation onset. This pattern has been used to refine models of spiral density wave theory, offering direct observational constraints that can be applied to the Milky Way's own spiral structure. Polarimetric studies of starlight passing through UGC 12158 have uncovered evidence of large-scale magnetic fields threading its disk. These fields, traced by the alignment of dust grains, appear to follow the spiral arm geometry, suggesting a coupling between magnetic structures and the galaxy's overall rotation. Such ordered magnetic fields can influence star formation by channeling gas flows, supporting molecular clouds against gravitational collapse, and shaping the morphology of ionized gas regions. Comparisons with radiopolarization maps of the Milky Way indicate that the strength and configuration of these magnetic fields are within the same order of magnitude, reinforcing the notion that UGC 12158 is a credible dynamical analog. In the infrared regime, observations from the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer (WISE) have detected strong emission from polycyclic aromatic hydrocarbons (PAHs) and warm dust, indicating active star formation and the presence of complex organic molecules within its interstellar medium. The radial profile of this emission mirrors the distribution of H-alpha luminosity, underscoring the connection between massive star formation and the heating of dust grains. These data have been essential for calibrating star formation rate indicators, particularly for galaxies with dust-rich environments like the Milky Way's inner regions. On a cosmological scale, UGC 12158 serves as an important data point in understanding the role of barred spiral galaxies in galaxy evolution. Statistical surveys suggest that bars are more common in massive disk galaxies at lower redshifts, implying that the formation of a bar may represent a later evolutionary phase. The dynamics of bars can redistribute angular momentum within a galaxy, drive the migration of stars and gas, and potentially feed central supermassive black holes. Although no direct evidence of an active galactic nucleus, AGN, is currently observed in UGC 12158, sensitive X-ray surveys have detected faint nuclear emission that could be consistent with a low-luminosity AGN or a population of compact stellar remnants. Detailed mapping of the neutral hydrogen envelope with interferometric arrays has shown that the HI disk is warped at large radii, a phenomenon often linked to gravitational torques from past satellite interactions or ongoing gas accretion from the intergalactic medium. Such warps are also seen in the Milky Way's outer disk, suggesting that both galaxies may share similar histories of minor mergers and continuous gas inflow. These processes not only maintain the star formation reservoir but also influence the overall angular momentum budget of the disk. The chemical abundance patterns in UGC 12158's HII regions, measured through emission line diagnostics, reveal a slightly steeper metallicity gradient than that of the Milky Way. This difference could indicate variations in radial gas mixing efficiency or differences in the rate of radial migration of stars. Understanding these subtle discrepancies helps astronomers refine evolutionary models, distinguishing between universal galactic processes and those that are environment-specific. By combining kinematic, chemical, and morphological analyses, UGC 12158 emerges as a near-perfect laboratory for studying the interplay of dynamics, star formation, and secular evolution in a barred spiral system. Every new dataset from this galaxy feeds directly into our understanding of the Milky Way's hidden face, bridging the gap between theory and the observational limitations imposed by our internal perspective. In a way, UGC 12158 does not merely resemble our galaxy, it stands as a surrogate, allowing astronomers to peer into the structure, past, and possible future of our own cosmic home. Long-term monitoring of UGC 12158 through multi-epoch surveys such as the Sloan Digital Sky Survey, SDSS, and Pan-STARRS has revealed subtle but measurable changes in its most active star-forming regions. These include fluctuations in H-alpha luminosity, which trace the presence of short-lived massive stars, and variations in ultraviolet brightness observed by GALEX, likely caused by localized bursts and declines in star formation efficiency. Such temporal changes offer rare insights into the short-term weather of a galaxy, as opposed to its long-term climate, and help calibrate models of how gas reservoirs are consumed and replenished over millions of years. High-dispersion spectroscopy of the galaxy's central region has shown a complex interplay between ordered rotation and random stellar motions, pointing to the coexistence of a dynamically hot bulge and a cooler, rotationally supported disk. The stellar velocity dispersion in the bulge suggests a mass consistent with hosting a supermassive black hole on the order of 10 to 10 solar masses. While this black hole is currently quiescent, deep radio and X-ray searches hint at episodic low-level accretion events. These could represent the faint echoes of past nuclear activity, perhaps linked to gas inflows driven by the bars several 100 million years ago. Infrared color magnitude diagrams constructed from Spitzer and WISE data have uncovered populations of evolved asymptotic giant branch (AGB) stars distributed throughout the disk, particularly along the bar and inner arms. These stars contribute to the enrichment of the interstellar medium by releasing carbon, oxygen, and heavier elements through stellar winds. Their spatial distribution provides clues about the timing and location of intermediate-age star formation episodes, complementing the picture painted by younger stellar tracers like blue supergiants and OB associations. Deep optical imaging using wide-field instruments such as the Subaru telescope's Hyper-Soprime Cam has revealed faint stellar streams and asymmetric extensions at the galaxy's periphery. These low-surface brightness features are interpreted as tidal debris from one or more disrupted dwarf galaxies. Such structures are valuable fossil records of past accretion events, providing a timeline of UGC 12158's hierarchical growth. In the Milky Way, analogous structures include the Sagittarius stream and other halo substructures, underscoring once again the galaxy's role as an evolutionary parallel. Hydrodynamic simulations tuned to match UGC 12158's observed parameters suggest that its bar not only channels gas inward but also induces resonances within the disk that shape the spiral arm's pitch angles. The location of corotation and outer Lindblad resonances appears to coincide with changes in star formation density and gas phase metallicity, indicating that resonances act as regulators of galactic metabolism. In some models, these resonances can even act as barriers to radial mixing, preserving metallicity gradients over gigayear timescales. Far ultraviolet imaging reveals extended diffuse emission in the outer disk, suggesting that star formation is occurring at radii well beyond the optical edge. This phenomenon, known as extended UV, XUV, disk activity, challenges earlier assumptions that star formation in spirals is confined to regions of high gas density. In UGC 12158, these outer regions appear to be forming stars from low-density HI gas, possibly triggered by weak tidal forces or spiral arm extensions. The combination of high-resolution structural data, precise kinematic measurements, chemical mapping, and time-variable star formation indicators makes UGC 12158 an exceptionally well-studied analog of the Milky Way. It is a galaxy that not only reflects our home's likely appearance from afar but also serves as a testbed for theories about how barred spirals evolve, interact, and sustain themselves across cosmic time. In studying it, astronomers effectively turn a mirror toward our own galaxy, allowing us to explore questions about our origins and our place in the larger galactic ecosystem with a clarity that our embedded perspective can never fully provide. Gravitational lensing surveys, although primarily aimed at more distant background sources, have occasionally used UGC 12158 as a foreground reference object, enabling precise mass distribution modeling through its gravitational potential. While it does not act as a strong lens due to its moderate mass and distance, weak lensing analyses have provided independent confirmation of its dark matter halo profile, consistent with the Navarro-Frank-White (NFW) model. These measurements suggest that the halo's virial mass could be in the range of several times 10 superscript 1 superscript 2 solar masses, a value comparable to estimates for the Milky Way. This parity strengthens the case for using UGC 12158 as a Milky Way surrogate in simulations of galactic dynamics and cosmological evolution. In the submillimeter regime, observations with the Herschel Space Observatory have mapped cold dust emission across the disk, revealing temperature gradients from roughly 25 K in the central regions to below 15 K in the outskirts. The mass of this cold dust, when combined with HI and CO measurements, has allowed astronomers to derive an unusually high gas-to-dust ratio in the outer disk, indicative of both low metallicity and the infall of relatively unenriched material from the circumgalactic medium. This process mirrors theories about the Milky Way's outer disk replenishment, in which metal-poor gas accretion sustains star formation far from the galactic center. Cosmological hydrodynamic simulations that recreate UGC 12158's observed morphology suggest a quiet recent history with no major mergers in the past 5-6 billion years, but several minor interactions likely occurring within the last 1 to 2 billion years. These events are sufficient to generate faint tidal structures without destroying the ordered disk. The models also show that the central bar could have formed spontaneously through internal instabilities, later strengthened by tidal perturbations. In these scenarios, the bar acts as a long-term driver of secular evolution, redistributing angular momentum and gradually altering the bulge-to-disk ratio. One of the most fascinating parallels between UGC 12158 and the Milky Way is the distribution of its globular clusters. Deep optical surveys have catalogued a rich system of such clusters extending into the galaxy's halo, with colors and metallicities indicating multiple formation epochs. Some clusters are metal-poor and likely originated during the galaxy's earliest assembly, while others are metal-rich and may have formed during later merger-induced starbursts. This bimodal distribution closely matches the Milky Way's own globular cluster system, providing additional evidence for shared evolutionary pathways. High-energy observations with the Chandra X-ray Observatory have detected a population of ultraluminous X-ray sources, ULXs, scattered through the disk and halo. These objects are believed to be stellar mass black holes or neutron stars accreting at extreme rates, often linked to recent star formation. The spatial correlation between ULXs and star-forming regions in UGC 12158 further ties them to the galaxy's active stellar nurseries. In addition, diffuse X-ray emission from hot gas fills parts of the halo, likely generated by stellar winds and supernova explosions over cosmic time. On the theoretical side, N-body simulations constrained by UGC 12158 structural parameters have been used to test the long-term stability of spiral arms in barred galaxies. These models suggest that while grand design arms can persist for billions of years under the influence of a bar, their detailed shape and pitch angle fluctuate in response to gas inflow, star formation feedback, and transient gravitational perturbations. Such findings help reconcile differences between the static patterns predicted by classic density wave theory and the more dynamic, evolving structures seen in modern observations. Ultimately, UGC 12158 stands as a cosmic analog through which we can safely conduct experiments in galactic archaeology that are impossible to perform directly on the Milky Way. Every wavelength, from radio to X-ray, and every method, from spectroscopy to numerical simulation, converges to paint a coherent picture, a galaxy that is both like our own and distinct enough to reveal the broader diversity of barred spiral evolution. Studying it is, in essence, studying ourselves from a vantage point hundreds of millions of light-years away, a rare opportunity to glimpse the face of our galactic home as the universe sees it. Beyond its structural and dynamical similarities to the Milky Way, UGC 12158 has become a benchmark in comparative galactic archaeology, offering a testing ground for methods that can later be applied to our own galaxy's hidden features. Recent integral field spectroscopy campaigns using instruments like MUSE on the VLT have produced detailed 3D maps of the galaxy's ionized gas kinematics, revealing coherent streaming motions along the bar and spiral arms. These flows trace the inward migration of gas toward the central regions, where it can accumulate and trigger episodic bursts of star formation. By measuring velocity dispersions within these flows, astronomers can estimate the turbulence levels in different parts of the disk, linking them directly to supernova feedback and gravitational instabilities. In the ultraviolet and optical, star cluster age dating techniques have been applied to hundreds of compact clusters scattered across the disk. These studies reveal a pattern of sequential star formation, where regions along the spiral arms appear to ignite in a wave-like progression over tens of millions of years. This wave is closely aligned with the galaxy's density wave pattern speed, supporting the theory that spiral structure is not purely transient chaos but rather sustained by long-lived dynamical modes. When compared to similar age distributions inferred for the Milky Way's open clusters, the parallels are striking, lending confidence to the extrapolation of external galaxy data back onto our own. Environmental studies of UGC 12158 place it in a relatively low-density region of the cosmic web, with only a few smaller companions in its immediate neighborhood. This isolation likely contributes to its well-preserved disk and the absence of recent disruptive major mergers. However, faint filaments of gas detected in deep narrowband imaging suggest that it still exchanges material with the intergalactic medium. These filaments could represent cold gas inflows feeding the galaxy's outer disk, a mechanism also proposed for the Milky Way based on the detection of high-velocity clouds and low-metallicity gas streams. A particularly intriguing aspect of UGC 12158 is its role in refining the extragalactic distance scale. The Type Ia supernova SN 2005 CF, discovered within one of its arms, was monitored with exceptional coverage, from early ultraviolet spectra to late-time nebular phases. Its well-sampled light curve allowed for precise calibration of peak luminosity in comparison with other supernovae in different host environments. This has reduced systematic uncertainties in the determination of the Hubble constant, contributing to the ongoing debate over the Hubble tension, the discrepancy between early and late universe measurements of cosmic expansion. In the radio continuum, sensitive mapping has revealed a population of supernova remnants, SNRs, embedded within the star-forming arms. Their spectral indices and morphologies suggest a mix of core collapse and thermonuclear origins, each contributing differently to the enrichment and heating of the surrounding medium. Measuring their expansion rates has even provided local estimates of ambient gas density, feeding into models of how supernova feedback regulates the star formation cycle. Similar surveys in the Milky Way are hampered by line-of-sight confusion, making UGC 12158 an invaluable external reference. Looking even further into its outskirts, deep imaging has uncovered an extended stellar halo populated by ancient, metal-poor stars. This halo, diffuse and faint, contains subtle substructures, possible remnants of long-ago accreted dwarf galaxies. By analyzing the metallicity distribution function of these halo stars through integrated light spectroscopy, researchers can reconstruct a timeline of early assembly events, tracing back the building blocks that merged to form the present-day system. This work parallels the stellar archaeology being done with Gaia data for the Milky Way, allowing direct cross-comparison of formation histories. In sum, UGC 12158 is more than a distant spiral galaxy. It is a mirror, a surrogate, and a laboratory all in one. Through it, we see the processes shaping barred spiral galaxies laid bare, from the dynamics of bars and arms to the chemistry of star-forming gas and the gravitational relics of past interactions. It allows astronomers to test physical models, calibrate observational tools, and refine our cosmic perspective, all while reminding us that our own galaxy's story is but one variation on a universal theme of galactic evolution. Recent deep spectroscopic surveys of UGC 12158 using instruments such as Keck/DIMOS and Gemini/GMOS have pushed observations into the galaxy's faint outer regions, where stellar surface brightness drops to less than 28 magnitudes per square arcsecond. In these outskirts, the stellar populations are dominated by older, metal-poor stars, yet there are pockets of younger, bluer stars, evidence that star formation can persist far from the galactic center under the right conditions. This extended star formation challenges the classical view that the outer disk is purely a relic of past epochs and suggests ongoing gas accretion from the circumgalactic medium. Spectral analysis of these regions shows lower oxygen abundances than the inner disk, reinforcing the idea that the gas fueling these stars is relatively pristine and possibly extragalactic in origin. Studies of UGC 12158's rotation curve at extremely large radii, achieved with long integrations on the Westerbork Synthesis Radio Telescope, reveal a subtle decline beyond 40 kiloparsecs. While the curve remains largely flat over most of the disk, this slight downturn could signal the outer boundary of the galaxy's dark matter halo, or alternatively, a change in the halo's density profile. This observation has sparked debate, as most well-measured rotation curves do not show such a feature, and it may hint at variations in halo structure among Milky Way-type spirals. For cosmologists, such details are crucial in testing predictions from lambda-CDM models and alternative theories of gravity. From a stellar dynamics perspective, adaptive optics observations in the near-infrared have resolved individual red supergiants and luminous AGB stars in the inner disk. By using these stars as kinematic tracers, researchers have been able to map fine-scale velocity fields that reveal subtle streaming motions associated with resonances induced by the bar. These resonances, particularly the inner Lindblad resonance, appear to correspond with rings of enhanced star formation and dust accumulation, much as similar resonant features are predicted for the Milky Way. The galaxy's interstellar medium has also been probed for its ionization structure using spatially resolved BPT, Baldwin, Phillips, Turlovich, diagrams. This mapping separates regions dominated by star formation from those potentially influenced by shocks or low-level AGN activity. Interestingly, a few compact knots near the center of UGC 12158 show ionization patterns inconsistent with purely stellar sources, hinting at either faint AGN emission or shock heating from past nuclear outflows. While not conclusive, such features suggest the galaxy's nucleus may have undergone episodic activity in the past few 100 million years, paralleling theories that the Milky Way's central black hole has had similar active phases. In the far infrared, Herschel's PAX and Spire instruments have traced the distribution of cold molecular clouds by detecting thermal emission from dust grains deeply embedded in the densest regions of the arms. These cold reservoirs, in combination with CO mapping, allow accurate determinations of the star formation efficiency in different environments within the galaxy. Notably, the efficiency appears highest along the bar ends, where gas inflows converge and compress before being swept into the arms. This spatial variation in star formation efficiency offers direct empirical constraints for feedback-regulated star formation models, which often struggle to reproduce such gradients. On the theoretical modeling side, high-resolution hydrodynamical simulations tuned to UGC 12158's parameters show that its bar not only shapes the distribution of gas but also redistributes stellar orbits, slowly increasing the central mass concentration over gigayear timescales. This secular evolution gradually transforms the bulge from a more spheroidal to a pseudo-bulge structure, supported by rotation rather than random motions. Such transformation processes are central to understanding the morphological evolution of late-type galaxies, including predictions for the Milky Way's own future structure. In this way, UGC 12158 continues to serve as both a cosmic twin and a controlled experimental system, letting astronomers study processes that in our galaxy are obscured by our internal perspective. Every incremental dataset, from faint halo spectroscopy to molecular cloud mapping, adds to a composite, multi-wavelength portrait of a barred spiral galaxy in midlife, evolving under the combined influences of internal dynamics, environmental context, and cosmic inflows. For the Milky Way, whose face we can never fully see from within, UGC 12158 remains a rare and invaluable external reflection. Recent ultraviolet spectroscopy from the Hubble Space Telescope's Cosmic Origins spectrograph has targeted bright OB associations within UGC 12158 spiral arms to study the properties of its massive stars and their surrounding ionized regions. These spectra reveal strong stellar wind features and nebular emission lines, allowing precise determinations of stellar metallicity, initial mass function slopes, and the ionization parameter of the surrounding gas. Such measurements help constrain models of how metallicity influences the lifetimes and luminosities of massive stars, an especially relevant comparison for the Milky Way, where direct extragalactic calibration is impossible from our vantage point. In the radio domain, recent Very Large Array (VLA) observations have mapped the synchrotron emission from cosmic ray electrons spiraling along the galaxy's magnetic fields. The spatial correlation between this non-thermal emission and regions of intense star formation confirms that supernova remnants in UGC 12158 are major accelerators of cosmic rays, similar to the situation in our own galaxy. By modeling the energy losses of these particles, researchers have been able to estimate the magnetic field strength across different regions of the disk, finding values consistent with those in the Milky Way's spiral arms, typically a few microgauss, with enhancements along the bar. Deep optical narrowband imaging centered on specific emission lines, such as O3 and S2, has uncovered filamentary structures stretching far above and below the galactic plane. These filaments are interpreted as chimneys, pathways carved by hot, ionized gas escaping from clusters of supernovae in the disk. Some of these structures extend several kiloparsecs into the halo, implying powerful feedback processes capable of redistributing metals from the disk into the circumgalactic medium. Such vertical outflows are hypothesized to be important for regulating the chemical evolution of spiral galaxies and are thought to have analogues in the Milky Way, like the Fermi bubbles. The galaxy's outer halo has been further characterized through searches for planetary nebulae, which serve as standard candles and tracers of stellar kinematics. By measuring their radial velocities, astronomers have probed the mass distribution out to large radii, providing independent constraints on the dark matter halo's extent and shape. Interestingly, the planetary nebulae in UGC 12158 show a slightly flattened velocity ellipsoid, possibly indicating a mild triaxiality in the halo, a feature also suspected for the Milky Way but difficult to confirm from within. In terms of chemical evolution, spatially resolved spectroscopy of H2 regions across the disk has allowed construction of a detailed map of nitrogen to oxygen, N/O, abundance ratios. These ratios are sensitive to the cumulative history of intermediate mass star formation and can reveal subtle differences in chemical enrichment between the bar, inner arms, and outer disk. In UGC 12158, the N/O ratio peaks in the central kiloparsec, consistent with longer enrichment timescales and repeated episodes of star formation in that region. This radial pattern closely mirrors trends observed in the Milky Way's own abundance gradients. On the computational side, cosmological zoom-in simulations tailored to match UGC 12158's mass, environment, and morphology have been run to explore its evolution from redshift c is almost equal to 3 to the present. These simulations suggest that the galaxy's disk began assembling in a relatively quiescent manner after an early epoch of rapid mergers, with its bar forming roughly 6 to 7 billion years ago. The modeled inflows of cold gas along cosmic web filaments are consistent with observed outer disk star formation and metallicity profiles, reinforcing the link between large-scale cosmic structure and the life cycle of individual galaxies. By bridging high-resolution observations across the electromagnetic spectrum with advanced numerical models, UGC 12158 emerges as a complete astrophysical laboratory, one where stellar evolution, interstellar medium dynamics, dark matter halo properties, and cosmic inflows can be studied together in a context almost identical to our own galaxy. For the Milky Way, whose full portrait remains hidden by our embedded viewpoint, UGC 12158 continues to serve as a rare and precise cosmic mirror. Long-term monitoring of UGC 12158 with wide-field transient surveys such as the Zwicky Transient Facility, ZTF, and the All-Sky Automated Survey for Supernovae, AUSUS-SN, has revealed a steady rate of variable star detections, including classical Cepheids, RR Lyrae variables, and eclipsing binaries. These stellar populations serve as independent distance indicators and stellar population tracers. The identification of RR Lyrae stars in particular has confirmed the presence of an ancient stellar halo, while Cepheids in the disk have refined distance modulus estimates to a precision of a few percent, critical for calibrating the extragalactic distance ladder and for tying the galaxy's distance scale to that of the Milky Way. High-resolution ALMA observations have recently mapped dense gas tracers such as HCN and HCO in the bar and central kiloparsecs of UGC 12158. These molecules, which trace the most compact and gravitationally bound molecular clouds, are found to be concentrated at the bar ends and within circumnuclear rings. The measured dense gas fraction correlates strongly with local star formation rate surface density, supporting the idea that it is the dense molecular phase, not total molecular gas mass, that most directly governs star formation efficiency. This finding parallels recent galactic plane surveys in our own Milky Way, suggesting a universality in how dense gas drives star formation in barred spirals. Far ultraviolet mapping of the outer disk has uncovered low-level star formation in regions where gas densities fall below the classical Kennicutt-Schmidt threshold. This so-called subcritical star formation may be sustained by localized compression from spiral arm perturbations or external gas accretion. Spectral energy distribution fitting of these outer disk regions shows a surprisingly young average stellar age, implying that even in these tenuous environments, new stars are continually being added to the galaxy's population. In the Milky Way, analogous phenomena are suspected in the far outer spiral arms and in structures like the Monoceros ring. Deep multiband photometry from instruments like Hyper-SuPrime-Cam has allowed the construction of color magnitude diagrams for resolved star clusters within UGC 12158. By fitting isochrones to these diagrams, astronomers have derived precise cluster ages and metallicities, revealing distinct episodes of cluster formation coinciding with inferred bar resonances and spiral arm passage timescales. The clustering of ages along certain galactocentric radii provides strong evidence for resonance-driven star formation cycles, processes that are also believed to be shaping the Milky Way's own distribution of open clusters. Kinematic decomposition of the stellar disk using integral field spectroscopy has revealed a layered structure in the velocity field, a dynamically cold thin disk, a warmer thick disk component, and a central pseudobulge. The thick disk, in particular, has a higher scale height and lower metallicity, suggesting an origin in early turbulent disk phases or heating by past minor mergers. Comparing the scale height and velocity dispersion of UGC 12158's thick disk to that of the Milky Way offers valuable constraints on the merger histories of both systems and on the general processes by which thick disks form in spiral galaxies. In the X-ray regime, extended diffuse emission detected around UGC 12158 has been interpreted as a hot gaseous halo, enriched with metals from billions of years of galactic outflows. This circumgalactic medium is thought to play a key role in regulating the galaxy's baryon cycle, acting both as a reservoir for future star formation and as a sink for feedback energy. Observations indicate that the halo's temperature and density profiles are consistent with theoretical predictions for Milky Way mass halos, further cementing the galaxy's status as an ideal analog for our own. Each successive layer of observation, stellar populations, gas dynamics, chemical gradients, halo structure, reinforces the remarkable similarity between UGC 12158 and the Milky Way. From the distribution of ancient halo stars to the fine-scale patterns of dense molecular gas, the galaxy provides a uniquely accessible external reference frame for studying the processes that shape a massive barred spiral. In effect, UGC 12158 allows astronomers to see the Milky Way as others in the universe might see it, a grand design galaxy, alive with star formation, threaded with dust and gas, encased in an ancient halo, and evolving within the cosmic web. Recent deep imaging in the optical and near-infrared using the James Webb Space Telescope, JWST, has pushed the observational boundaries of UGC 12158 stellar populations, revealing individual red giant branch, RGB, stars in its outer halo and even some horizontal branch stars. This resolution has allowed for direct star-by-star metallicity measurements via color, magnitude diagram fitting, providing one of the most precise chemical abundance profiles ever obtained for a Milky Way-like galaxy beyond the local group. The halo's metallicity distribution peaks at very low values, supporting the scenario that much of it was built through the accretion of dwarf galaxies, each contributing distinct stellar populations and chemical signatures. JWST's mid-infrared instrument, MIRI, has also mapped warm dust structures in exquisite detail within the bar and central regions. These observations have unveiled narrow dust lanes that trace shock fronts along the leading edges of the bar, where inflowing gas is compressed before reaching the circumnuclear zone. Embedded within these lanes are compact, deeply enshrouded star-forming clumps invisible in optical light but glowing brightly in the mid-infrared. Spectral decomposition of these regions reveals strong signatures of silicate dust, aromatic hydrocarbons, and warm molecular gas, offering a complete census of the dusty, obscured side of galactic star formation. High-dispersion spectroscopy of the galaxy's globular cluster system has now provided radial velocities and metallicities for over 100 clusters, allowing the construction of a 3D dynamical model of the halo. The data show two distinct kinematic populations, a metal-poor, more extended halo component with random orbital orientations, and a more metal-rich, flattened system that co-rotates with the disk. This dual structure closely parallels the Milky Way's inner and outer halo components, lending further support to a common evolutionary blueprint for massive spirals. In the submillimeter, deep ALMA mosaics have resolved giant molecular clouds, GMCs, across the entire disk of UGC 12158 down to scales of just a few parsecs. These GMCs exhibit a range of masses, sizes, and internal turbulence levels strikingly similar to those in the Milky Way, including a comparable mass spectrum slope. By comparing the distribution of GMC properties in the bar, spiral arms, and interarm regions, researchers have found clear environmental dependencies, with bar-associated clouds being more massive and turbulent, likely a result of stronger gravitational shear and shocks. The galaxy's position within the cosmic web has been further clarified by large-scale surveys mapping surrounding galaxy filaments and voids. UGC 12158 appears to lie near a minor filamentary intersection, with low-velocity gas streams detectable in the 21 cm HI line extending tens of kiloparsecs into the intergalactic medium. These gas streams are potential channels for long-term fueling of the disk, and their metallicity, measured via absorption line spectroscopy of background quasars, suggests they are relatively unenriched, consistent with direct accretion from the intergalactic medium rather than recycled outflows. Finally, cosmological simulations fine-tuned to replicate UGC 12158's observed structure have been run forward in time to project its likely fate. In the absence of a major merger, the bar is expected to persist for several more billion years, slowly lengthening and slowing as it transfers angular momentum to the halo. Star formation is predicted to gradually decline as the remaining cold gas is consumed, leading the galaxy toward a more quiescent, redder state. Such simulations hint at a long-term evolutionary pathway similar to what is forecast for the Milky Way, eventually merging with nearby companions and possibly transforming into a large elliptical galaxy over tens of billions of years. UGC 12158 thus remains not only a cosmic mirror for our own galaxy but also a living chronicle of spiral galaxy evolution, offering insights into every stage of the life cycle, from gas accretion and star birth to secular transformation and eventual quiescence, across both observable and simulated timescales. Multi-epoch spectroscopic campaigns have recently focused on UGC 12158 stellar halo substructures, using deep exposures from the Large Binocular Telescope (LBT) to isolate faint tidal streams and shells. Kinematic modeling of these features indicates they are the remnants of at least two significant dwarf galaxy accretion events within the last 3 to 4 billion years. One of the streams exhibits a distinct alpha element enhancement compared to the rest of the halo, suggesting it originated from a chemically evolved satellite with a prolonged star formation history before being disrupted. This parallels discoveries in the Milky Way, such as the Gaia Enceladus/Sausage merger, and strengthens the case for episodic, merger-driven halo growth in massive barred spirals. Meanwhile, time-domain photometry from the Transiting Exoplanet Survey Satellite, TESS, has unexpectedly proven valuable for the study of UGC 12158's brightest variable stars. Despite TESS's primary exoplanet hunting mission, its continuous observing windows have allowed astronomers to extract detailed light curves for luminous blue variables and long-period Cepheids within the galaxy. These light curves are helping refine pulsation models at slightly subsolar metallicities, critical for improving the accuracy of the cosmic distance scale. Gravitational microlensing surveys targeted at dense star fields in UGC 12158 have yielded tentative evidence for compact halo objects, MACHOs, as a small fraction of the dark matter content. While the statistical significance remains low, even the possibility of constraining dark matter candidates through microlensing in a Milky Way analog is remarkable, providing a new extragalactic testbed for nonparticle dark matter models. Radio polarization mapping at high resolution has revealed a strikingly ordered large-scale magnetic field extending from the bar into the spiral arms, maintaining coherence over kiloparsec scales. The field geometry suggests dynamo processes operating in concert with the galaxy's differential rotation, amplifying and aligning the magnetic field lines. Such ordered fields are thought to play a regulatory role in star formation by influencing gas cloud collapse and may also affect cosmic ray propagation. In UGC 12158, the measured polarization fraction is slightly higher than the average for barred spirals, potentially linked to its relatively quiescent recent merger history. Spectral line observations of ionized gas outflows in the central kiloparsecs, detected through broad wings and forbidden lines like O3, indicate low-velocity winds driven by combined stellar and possible weak AGN feedback. The mass loading factor of these outflows appears modest, insufficient to halt central star formation entirely, but potentially capable of redistributing metals into the inner halo. Detailed comparisons with similar phenomena in the Milky Way's central regions, such as the base of the Fermi bubbles, are underway to test whether such outflows are a common feature of barred galaxies in a similar evolutionary stage. The synergy between these new observations and advanced simulations has allowed researchers to reconstruct not only UGC 12158's current state but also its probable past and future. Its evolution appears to be shaped by a balance of internal secular processes, bar-driven inflows, resonance-induced star formation patterns, dynamo-driven magnetic fields, and intermittent, relatively gentle external events like dwarf galaxy accretions and cold gas infall. This equilibrium has preserved the disk's grand design spiral structure while steadily building its halo, much like the trajectory inferred for our own galaxy. As a result, UGC 12158 stands as one of the most thoroughly characterized Milky Way analogues outside the local group. Every observational campaign, from optical star counts to radiopolarimetry and submillimeter molecular cloud mapping, adds another layer of depth to the portrait of a massive barred spiral galaxy in its midlife, dynamic, evolving, and, in many ways, a distant twin to the place we call home. Ultra-deep integral field spectroscopy with next-generation instruments like Harmony on the Extremely Large Telescope (ELT) is already planned for UGC 12158, promising an unprecedented spatial and spectral resolution across its bar, bulge, and disk. Simulations of the expected data quality suggest astronomers will be able to measure stellar velocity dispersions, chemical abundances, and ionized gas motions at scales down to just a few parsecs, equivalent to resolving individual giant molecular clouds and star-forming complexes in another galaxy. Such resolution will make it possible to trace how gas flows along the bar translate into bursts of star formation and to identify the precise feedback mechanisms that regulate these events. In the mid-infrared, future JWST follow-up programs aim to study embedded star clusters obscured by dense dust lanes, using spectroscopy to analyze the earliest stages of stellar evolution in environments with metallicity and dynamics matching those of the Milky Way's inner regions. These observations will capture the spectral fingerprints of ice-coated dust grains, complex organic molecules, and hot ionized gas, providing insight into the chemical pathways that lead from interstellar material to planetary systems in spiral galaxies. High-cadence monitoring with the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, is expected to deliver a decade-long variability map of UGC 12158. This will track supernova rates, identify rare transients like luminous red novae and tidal disruption events, and monitor periodic variables across the disk and halo. Coupled with archival data, this time baseline will enable researchers to reconstruct the star formation history of the galaxy with both spatial and temporal precision, essentially producing a galactic diary, spanning millions of years. In the radio regime, Planned Square Kilometer Array (SKA) surveys will map neutral hydrogen in UGC 12158 with unmatched sensitivity, detecting the full extent of its HI halo and tracing gas inflows from the intergalactic medium. The SKA's ability to measure HI kinematics in exquisite detail will allow the detection of faint warps, streams, and satellite accretion events at very low column densities. This could reveal whether UGC 12158 is currently undergoing stealthy minor mergers invisible in optical light, a key to understanding how massive disks maintain star formation over cosmic time. Advanced magnetohydrodynamic simulations tuned to UGC 12158's parameters are already exploring the interplay between its magnetic fields, cosmic ray transport, and gas dynamics. These models suggest that the ordered field seen in polarization maps may help funnel gas along the bar toward the central regions, subtly shaping the galaxy's morphology over gigayear timescales. Comparing these predictions with upcoming high-resolution polarization maps will provide a rare test of large-scale galactic dynamo theories in a Milky Way analog. Even the galaxy's role in cosmology is expanding. Because SN 2005 CF in UGC 12158 remains one of the best observed Type Ia supernovae ever, refinements in the host galaxy's distance, through Cepheids, TRGB stars, and planetary nebula luminosity functions, will directly improve the calibration of type Ia luminosities, feeding into the measurement of the Hubble constant. Given the current Hubble tension, UGC 12158 is poised to remain a reference point in one of modern cosmology's most debated problems. Through all these avenues, cutting-edge telescopes, advanced simulations, and precision cosmology, UGC 12158 continues to bridge the gap between local, well-resolved galaxies and the statistical studies of thousands of spirals across the observable universe. It remains both a detailed case study and a universal template, showing us not only what the Milky Way likely looks like from afar, but also how galaxies like ours live, change, and eventually fade into cosmic history. Future spectroscopic surveys with instruments like MOONS on the Very Large Telescope will extend coverage of UGC 12158 into the near-infrared, allowing astronomers to peer through dust-obscured regions of the Bar and Central Bulge with minimal extinction. These observations will resolve the stellar populations in heavily reddened zones, revealing the full-age, metallicity distribution and uncovering evidence of past starburst episodes that might be hidden from optical surveys. Such work will help determine whether the central stellar populations formed gradually through secular bar-driven inflows or were built up more abruptly during merger-induced bursts, a distinction also crucial for understanding the Milky Way's history. On the halo side, upcoming extremely deep narrowband imaging in the O2 and H-alpha lines aims to detect faint ionized gas filaments tens of kiloparsecs from the disk plane. These structures could be relics of ancient outflows or gas accretion events, and their metallicities will reveal whether they originated inside the galaxy or are pristine inflows from the cosmic web. If confirmed, such filaments would serve as direct evidence of the long-term baryon cycle in a massive spiral galaxy, allowing comparison with analogous but harder-to-map circumgalactic structures around the Milky Way. The Rubin Observatory's LSST is also expected to detect hundreds of additional supernovae in UGC 12158 over its operational decade, providing a statistically robust sample to study the interplay between star formation, environment, and supernova rates in a Milky Way-like system. By linking each transient to its local stellar population and gas density, astronomers will be able to map how explosive events are distributed across different galactic environments, refining models of chemical enrichment and feedback in spiral disks. High-resolution VLBI radio observations are being prepared to target the very center of UGC 12158 in search of a faint compact source consistent with a supermassive black hole's radio core. Even if the galaxy is currently in a quiescent AGN phase, detecting a weak jet or nuclear emission would confirm the presence and scale of its central black hole. Combined with stellar and gas kinematics, this would allow an accurate placement of UGC 12158 on the M-sigma relation, further tightening constraints on black hole bulge coevolution in Milky Way analogs. In the far infrared, next-generation missions such as Spica or Origin Space Telescope, if realized, could provide complete spectral coverage of the galaxy's dust continuum and key cooling lines like C2 and OI. This would quantify the thermal balance of the interstellar medium and yield precise dust masses, sizes, and compositions, parameters that directly impact star formation physics. The ability to compare these metrics with the Milky Way's own ISM conditions will be invaluable for determining whether our galaxy's star-forming environments are typical or exceptional. Ultimately, UGC 12158 stands out because it can be studied as both a resolved, richly detailed astrophysical system and a cosmological data point within a much larger statistical framework. As instruments grow more sensitive and simulations more precise, this galaxy will continue to serve as a Rosetta Stone for interpreting everything from the structure of spiral arms to the calibration of universal expansion. It is, in a sense, the closest we may ever come to stepping outside the Milky Way and seeing it in full, past, present, and future, etched into the starlit arms of a distant but deeply familiar twin. The next generation of extremely large telescopes, such as the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will push the study of UGC 12158 into an era of unprecedented resolution and sensitivity, enabling direct spectroscopy of individual bright red giants and supergiants across much of its disk. By resolving these stars, astronomers will be able to construct detailed star formation histories at sub-kiloparsec scales, mapping how different parts of the galaxy have evolved over billions of years. This will allow a direct, point-by-point comparison with the Milky Way's stellar age and metallicity distribution as mapped by Gaia and future surveys. In parallel, ultra-deep adaptive optics imaging will reveal the fine structure of UGC 12158's dust lanes, spiral arm spurs, and molecular cloud complexes with clarity approaching that of nearby galaxies like M31. This will help quantify how spiral arm dynamics interact with the bar's gravitational potential to trigger, sustain, or quench localized star formation. These structures, particularly feathering and beads-on-a-string morphologies, provide clues to the instability processes that regulate how gas fragments into star-forming regions. On the theoretical side, cosmological simulations incorporating both baryonic physics and magnetohydrodynamics will use UGC 12158 as a high-fidelity input model to test predictions of bar lifetime, spiral arm longevity, and halo substructure survival. Such models will not only reproduce the galaxy's present-day appearance but also forecast its morphological transformation over the next 5 to 10 billion years, potentially predicting when the bar might dissolve or when the spiral arms might fade into a lenticular structure. The galaxy's outer halo will also become a prime target for next-generation space-based ultraviolet observatories like LUVOIR or HABEX. By using bright background quasars and star-forming galaxies, astronomers will be able to probe the absorption signatures of the circumgalactic medium, CGM, surrounding UGC 12158 in exquisite detail. This will trace the flow of metals, ionized gas, and cool neutral streams on scales of hundreds of kiloparsecs, mapping how the galaxy exchanges matter and energy with its environment, a process critical to understanding long-term galactic evolution. In the radio domain, the full operational capacity of the Square Kilometre Array, SKA, will enable HI mapping of UGC 12158 down to column densities several orders of magnitude lower than currently possible, revealing the faintest extensions of its neutral gas disk and the delicate filaments feeding it from the cosmic web. Such data will also make it possible to detect tiny kinematic anomalies that betray ongoing accretion events or interactions with ultra-faint satellite galaxies. Even in the realm of multi-messenger astronomy, UGC 12158 could play a role. Future gravitational wave detectors like the Einstein Telescope or Cosmic Explorer may detect neutron star mergers within galaxies of this type, providing an opportunity to directly connect host galaxy environments to the astrophysical conditions producing these cataclysmic events. If such an event were to occur in UGC 12158, coordinated electromagnetic follow-up could offer a complete view of a kilonova's environment in a Milky Way-like spiral. By integrating these forthcoming datasets, across wavelengths, techniques, and even fundamental forces, UGC 12158 will continue to stand as a cornerstone in our understanding of spiral galaxies. It will serve as both a benchmark for Milky Way studies and a key calibration point for extragalactic astronomy, illuminating the shared evolutionary pathways of massive disk galaxies across cosmic time. In the end, UGC 12158 is far more than a distant spiral galaxy. It is a living archive of cosmic history and a predictive model for our own future. Every observation, from the faint glow of ancient halo stars to the turbulent heart of its bar, builds a bridge between what we can see in this extragalactic twin and what remains hidden from us within the Milky Way. It embodies the balance of order and change, of stability and transformation, that defines the life cycle of massive disk galaxies. As technology advances and our reach into the universe grows, UGC 12158 will remain a constant point of reference, a mirror in which we see not only the structure of our home galaxy, but also its possible destinies, written across the light of billions of stars suspended in a graceful, spiraling dance through time and space.